So thank you all very much for tuning in. I've got the fan on in the background, so if it's cutting in the mic, do holler and I can just adjust that. So yes, I'm going to talk a little bit about the oft under-discussed Lunar Granulites suite and how it records high temperature metamorphism within the lunar crust. So there we go. So yes, so the granulite metamorphism, it's the result of high temperature, and when we say high temperature, we mean peak metamorphic temperatures are around about 1,000 degrees Celsius, that causes recrystallization of hyaline lithologies. Now, the granulites, they're not a particularly dominant lithology in the Apollo collection. They're mostly present as small fragments and clasts within breccias and soils. They're most dominantly found out of all the Apollo sample collections from 16 and 17, where a few larger hand sort of sized, if you will, specimens were collected, such as the one that's shown on the right hand side there. But so really, I guess all of these, this sort of suite begs the question really, you know, how does high temperature metamorphism like this take place within the lunar crust? What are the sort of mechanisms that allow this to take place? And these are important questions to ask, as these give important insights into how the lunar crust and how specifically the primary and secondary lithologies within the lunar crust are modified over geological time. So I'm just going to spend 2 slides quickly just talking a bit about what I mean when I say a granulite, as this term is slightly different to how it's used in terrestrial metamorphic geology. In terrestrial terms, there's a very specific temperature and pressure connotation, whereas these are solely the result of high temperature, not pressure. And so in this regard, they're a bit more similar to hornfels for those who are more familiar with terrestrial metamorphic petrology. So these have a wide variety of different textures that we see in the sample collection, and these are just a couple of examples, representative examples of some of the textures that we observe. On the right hand side, we see some sort of very nice granoblastic type textures, which is sort of classic recrystallization, where you've got plagies and olivines and pyroxenes intersecting at roughly 120-degree angles. Interestingly, there's also some poikilotic type textures, which particularly when they're these textures are found as small class, they can be quite difficult to identify these as belonging to the granulite suite, as opposed to, say, poikilotic impact melts. But more often than not, we see quite a lot of heterogeneity on thin section scales in terms of textures. You quite often see sort of more granoblastic type matrix with pockets of poikilotic type textures, showing that temperatures must have been elevated enough to result in very localized partial melting in some cases. And as I alluded to just now, these are the result of the metamorphosis of hyaline lithologies, and the chemistries show that the more ferroan examples are very similar to ferroan northosites. And this can be seen in the old classic plot of magnesium number and mafic minerals versus AN content in plagioclase. And the blue symbols here are the more ferroan examples from the granulite suite, and they fall very nicely in the fan field. The red samples are the more magnesium-rich subtypes, and these are a lot more similar in their composition to secondary plutonic rocks. They're not necessarily directly related to the MG suite. There's some subtle trace element differences that's represented on the right-hand plot here that mean they may not be directly related to the MG suite. The details of which are not too important for the purpose of this talk. The main take-home message really here is that the protoliths are a wide selection of both primary and secondary crustal lithologies. And the other important thing to note here as well is that they have elevated siderophile element abundances relative to their pristine counterparts, suggesting that the protoliths are somehow been in the mix with some kind of impact event. And so a lot of people have suggested that the direct protoliths, rather than pristine rocks, are somehow impact modified versions of these pristine lithologies. And so this loops us back round then to where in the crust is this high temperature metamorphism taking place, and what can we do to try and constrain some of these mechanisms that allow these granulites to form? And there are 2 sort of main hypotheses that have been put forward. The favorite and the one that seems the most airtime within the literature is that this high temperature metamorphism can take place around craters that are large enough to host impact melt sheets. And so the idea being, if you can imagine a nice thick and hot impact melt sheet, should have in principle the thermal conditions to heat the surrounding rock, either the megaregolith or on the crater walls, or some kind of megaregolith or fractured or brecciated material, or whatever material is sat below the impact melt sheet. I think it's important to also highlight that we can't discount the role that plutonic intrusions and basaltic sills and dikes may play in creating the sort of conditions necessary for granulite metamorphism. These are also hot bodies being intruded into the crust that may have the correct thermal properties to result in contact metamorphism around the edges. The one argument, however, that makes this slightly less likely is that these, in order to sort of preserve the elevated sidrophile element compositions, these can't be too deep in the megaregolith when the MG suite or whatever secondary plutonics are being intruded into the crust. They can't be, well, anyway, I'll gloss over that as I see the time is ticking down. So how can we approach this then for constraining the impact melt sheet thermal conditions? And so I'm going to basically look at titanium in orthopyroxene. If you can imagine a pyroxene, minor and trace element zoning can help constrain the impact melt sheet thickness by looking at how fast minerals diffuse at a high temperature. And this is because if you understand how fast a major and trace elements move throughout, diffuse throughout a mineral, then you can effectively use that speed of diffusion to estimate how long a mineral's been held at temperature. And what we see is a range of equilibration ages for these samples. We see a range of zonation patterns. Some suggest that some of these profiles show very little zoning, others show quite some nice diffuse zoning patterns. And ages effectively date the metamorphic duration from hundreds of years to tens of thousands of years. And we can do a bit of thermal modeling to then try and constrain what thickness of melt sheet we need to produce this sort of length of period of metamorphism. And so this is just a plot showing temperature versus depth we did some very simple heat flow modeling using the classic equation of Jaeger from the late 60s. So this modeling basically shows on this plot of temperature versus depth, 0 being the contact between the melt sheet and underlying rock. I can go into the details of this modeling a bit more in the discussion later on, as I can see I'm nearly out of time. I've only got a few more slides to go. But basically, this model also takes into account the fact that the melt sheet will cool over time. And so what the thermal modeling suggests is that after, say, 300 years, the bottom 100 meters of rock will be the appropriate kind of temperature for granulite metamorphism. And then when you consider the closure temperatures of titanium in pyroxenes, oh, this is actually the wrong slide. That figure is incorrect. I do apologize. I must have loaded an old version of the talk. This should actually read 4 kiloyears. This should actually read 2, and this should actually read 150. So I do apologize. But anyway, the point being that after the thermal modeling suggests that after 4,000 years, a 700 meter thick melt sheet will be able to produce temperatures that will allow titanium to diffuse in the pyroxenes for 4 kiloyears. So that's consistent. And we can use the melt sheet thicknesses and this type of thermal modeling to estimate crater diameter. And just in the interest of time, I'll just leave these general conclusions is that granulites have the potential to form in a very wide range of impact locations. Our titanium zonings that we observed in these granulites suggest that craters, that you can get granulite metamorphism in craters that range from 60 kilometers in diameter above, which is actually the majority of craters on the moon. And so actually granulite metamorphism, despite the fact that not being particularly common in the Apollo collection, it should be a very important lithology associated with impact structures on the moon. So apologies for running over slightly, and I'll leave that there.
Thank you very much, John.